Okay, in this section, we're going to look at rational expressions. This is the last voiceover for week 1. We will look at domains, simplifying, multiply, dividing, adding, subtracting, some compound fractions, rationalizing the denominator or the numerator, and avoiding common errors. Now, again, I just want to remind you that this is a review chapter, so hopefully, again, when you're looking at all this, you're like, yeah, I remember this, it's easy, no problem. If you have some areas that you don't quite remember, then it's up to you to go back and find some more materials to review those so that you won't have trouble as we move forward in the other sections. Here we have fractional expressions. So we have a fraction with an expression on the top and the bottom. We call them rational expressions whenever we have polynomials on both the bottom and the top, numerators and denominators. So here we have an algebraic expression, algebraic expression. Looking at a domain. In general, you can use this chart below to help you remember some basics about finding the domain. If you have a variable on the bottom of a fraction, this bottom cannot be 0. So you have to make sure that whatever you have in your domain, that you cannot have numbers that will be put in there that would become 0. If you have a square root, then you need to remember that that square root has to be greater than or equal to 0 because we're looking in the real number system. If that square root is on the bottom, then it also cannot be 0. So we take away equal to 0 because you can't have a 0 on the bottom of a fraction. So these basic concepts will help you to find domain. Looking at the following expressions, here we have a polynomial. Hopefully you remember that all polynomials are, their domains are from negative to positive infinity, all real numbers. We don't have to worry about any exclusions there. So we would just put all real numbers, or if we wanted to write it in interval notation, we would say from negative infinity to positive infinity. Oh, I'm getting a little rusty again using this little pad where I'm writing. Okay, there we go. All right, so either of these two answers. Now, B, if I look at this, I see that I have an algebraic expression on the bottom of a fraction, so I'm going to have to take a look at that to see what would give me 0 on the bottom, because that will not be in my domain. And then on this one, I see I have a square root on the top, so this top has to be greater than or equal to 0. And then the bottom, I cannot have 0 on the bottom, so it looks like I cannot put the number 5 in here. So let's take a look at how to examine these. All right, so the first one, as we said, is the set of all real numbers because it's a polynomial. The second one, we have to take a look at the bottom. When I factor the bottom, I see that if I placed 2 or 3 in for x, I will get 0. So I have to make sure that I identify that when I'm looking at my domain. I'm going to have to make sure that I say it's all x such that x cannot equal 2 and x cannot equal 3. Okay, so this is our set notation for it right here. In our last one, we have to take a look and see up here, we don't want this to be anything that is negative, so it has to be greater than or equal to 0. And on the bottom, I would get 0 if I put 5 in for x. So I have to keep both of those things in mind. So it's going to be for all x such that x is greater than or equal to 0. That's by the top. However, I have to say, and x cannot equal 5, because if it does, I'll get 0 on the bottom. Simplifying rational expressions. Okay, now, I thought I got everything out of here that said cancel, but apparently I didn't. So we're not going to say cancel. We're getting rid of this, and we're going to call this reduce. We are going to reduce. We are not canceling. Canceling means that you eliminate. We're not eliminating, we're just reducing it to a number 1. Okay, so this is reduce. Hopefully, if one pet peeve you remember from Dr. Miller is that you say reduce and not cancel. All right, here's an example. We want to factor the top and the bottom. We see that the top is a difference of perfect squares. We look at the bottom, we say factors of 2, that will give me positive 1. That's 2 and negative 1. And we factor. So here we have our factored result. We notice that we do in fact have x plus 1, or x minus 1, sorry, on the bottom. I was clicking my pen when I wasn't looking. Okay, so we're going to reduce these two because they reduce to 1, and this is what's left. Reduce. See, I did change it here. All right, got that? Now, multiplying and dividing rational expressions, I'm going to have a rational expression times a rational expression. So I multiply the tops and I multiply the bottoms. And sometimes I'll be able to reduce. And when I'm able to reduce, I'm going to have similar things either vertically, or I will have similar things that are diagonally to reduce. Like a bow tie. See the bow tie? All right, here's an example. So we have this rational expression multiplied by that rational expression. We want to factor them first. So we take our time and we factor. The first one we get x minus 1, x plus 3 on the top. I get x plus 4 quantity squared. That's a binomial square on the bottom. See how important it is to recognize that? Take out a 3 on the top, and I have x minus 1 on the bottom. Now, I want to take a close look and see what can I reduce. I can reduce either vertically or diagonally. I'm making my bow tie. Okay, so what can I reduce? Well, I see I have an x minus 1 here and an x minus 1 here. So I will reduce those to 1. I also have an x plus 4 here, and I have 2 of them here, so I'm going to just take one of them away and make this now just x plus 4, excuse me, to the first power. Then what's left? X plus 3 and 3 on the top, and x plus 4 on the bottom. There we go. Okay. Now, division, I just have to flip over the second one and use my multiplication rules. So here I have division. I want to factor everything, but I'm also going to flip this one over because when you divide fractions, you multiply by the reciprocal. So we flip it over. We factor everything on the top and everything on the bottom. And they put it all together, and that's fine. And now I'm going to want to reduce. I see an x minus 4, an x minus 4. I see an x plus 2 and an x plus 2. So what's left is x plus 3 on the top, x minus 2 on the bottom, and x plus 1 on the bottom. Adding and subtracting rational expressions. Here you have to be careful to find your LCD. All right, here we have 3 over x minus 1, and we have x over x plus 2. Neither one of these are the same, so that tells me that my LCD in this problem, my LCD is going to be each one of those. So it's going to be x minus 1 times x plus 2. So I look at my very first rational expression and I say which one is missing. Well, the x plus 2 is missing. So I'm going to multiply the top and bottom both by x plus 2. And let's see if they give that to us in this step. Yep, see here, I'm going to multiply the top and bottom both by x plus 2. I'm going to multiply the top and bottom of the second one by what's missing, which is x plus 1. So this is your first step right here. Then I'm going to simplify. I'm going to multiply, distribute this and multiply it. I'm not going to multiply this out yet because I want to wait to the end to see if I can reduce anything. But I am going to distribute this and distribute this and combine my numerators and see what I have then. Okay, I can see that I can reduce my 3x minus x. And I have x squared plus 2x plus 6. I want to check and see if this will reduce, but factors of 6 that I would add to get 2 does not work, so it is already fully factorable. Nothing else reduces, and that is my final answer. Okay, looking at LCDs again. Here I have 1 over x squared minus 1 minus 2 over x plus 1. If I factor these, I see that this is x minus 1, x plus 1, and I see that this is x plus 1, really, times another x plus 1 if we want to look at it for seeing what our LCD is. Might be a little easier if we spread it apart. Now, I have to have the same thing on both. So, I only have an x plus 1, x minus 1, x plus 1 here, but I have 2 here. So that means I'm going to add another x plus 1 to this one and an x minus 1 to this one. So, and they kind of skipped a step here, multiplying the top by x plus 1. And I didn't mind writing over that 1 because it was a 1. And this one I'm going to multiply by x minus 1. So if you didn't follow that, there you go. Okay, and that also put those both on the bottom as well. Okay, so this is now squared, and then this will now be another x minus 1 here. So I don't want to not say that. Whew, I'm getting sloppy. Okay, then once I put that together, I have my x plus 1 minus 2 times x minus 1, and then here's my LCD on the bottom. Now I want to simplify my top. I do not want to multiply the bottom because it might reduce. Okay, there is distributing through my -2 and dropping my parentheses. And now when I can combine everything, I have 3 minus x. I want to see if there's anything I can reduce with the bottom, and there is not. You should always check that. These examples are not showing that it will reduce, but oftentimes you will have more things that will reduce after you combine your numerators. All right, compound fractions. Compound fraction is where the numerator or denominator or both also have fractional expressions. So here's one. Now, whenever you see this, I want you to take one at a time Actually, I think I'll keep it with a pen. Take one at a time. Look at this. Make it into one expression. And then look at this and make it into one expression. So I take the top and I multiply it by y over y, and that'll give me x plus y over y. Then I take the bottom and I multiply it by x over, or I take x over x minus y over x. And why can I do that? Because this is 1. So I can make 1 into any form of 1 that I want to. So I can change this to be y over y. And I can change this to be x over x, as long as it's a form of 1. And the reason I'm doing that is because I need to have an LCD so that I can combine them. Okay, so here we have it. Now you need to remember that this fraction bar right here means division. Okay, so now I'm just taking two expressions, this divided by this. And so I flip it over and multiply by the reciprocal. And now I multiply the numerators and the denominator. Nothing reduces, so that'll be your answer. Solution 2, find the LCD of all the fractions of the expressions and multiply the numerator and denominator by it. You can do that as well. I prefer this first one, but if you want to do the second one, and you can look at the LCD being x over y. And if you multiply the whole thing by x over y, multiply the numerator and the denominator by it, then you will have that. That can be a little tricky, I think, just to pick out the LCD, because you're looking at the LCD of the top and the bottom as if you were actually adding these two expressions. But if you can see this very easily, then go for it and use that method. Here we factor in the end. Rationalizing the denominator or the numerator. Okay, if we have a radical, a square root, or sometimes even another root, cube root, fourth root, fifth root, and we have it in the numerator or denominator, we may want to get rid of that. So we do that by using what's called its conjugate. So notice that if I have a plus b times the square root of c, the conjugate, I'm just changing this sign to be negative. Why? Because when I multiply these together, I get a difference of squares, and then it will get rid of my radical, because the square root of c times the square root of c is c. So that is the whole reason why we use the conjugate, because we're making it look like a difference of squares. Okay, here we go. Rationalizing this denominator, the conjugate of the bottom would be 1 minus the square root of 2. So I multiply it in a form of 1, which means it'll be 1 minus square root of 2 over 1 minus square root of 2. That's a form of 1. When I do this, I now on the bottom have a difference of squares. So it'll be 1 squared, which is 1, and the square root of 2 squared, which is 2. Now, 1 minus 2, which is simply what this is, will give you negative 1 on the bottom. So now I will have 1 minus the square root of 2 over negative 1, and hopefully you will realize, well, I can just take this negative 1 and distribute it through, and my final answer will be negative 1 plus the square root of 2. No more fraction on the bottom. Now, sometimes you will still have a fraction. You'll have a number on the bottom, but you won't have a radical. Okay, there it is there again. And there that is, and distributing through the negative. Okay, avoiding common errors. This slide I love because it never fails when I'm teaching this class that I'll have these errors come up over and over again. If you have a parentheses and you're adding, you cannot just take square this plus square this. Remember, this is a binomial square, okay? It's a binomial square. You cannot just take the square into both. If you remember right, you're going to square the first, square the last, multiply them both together, and then double it. So you would have a squared plus 2ab plus b squared. All right, so this is wrong, this is right. Now, if you're multiplying, you can do that, and that's why we get confused sometimes. I can just take this into both. If we're multiplying, we have it under the square root, I can break it apart like that, no problem. But I cannot do that if I'm adding. This is wrong. Similarly, I could take the square root of a squared and get a, and take the square root of b squared and get b when I'm multiplying them together. But again, if I'm adding, I cannot do that. If I'm multiplying, I can just multiply the denominators together. But if I'm adding, I can't just put them together like this. I have to find the LCD. Multiplying again, I can reduce these two and I'm left with b. But if I'm adding and I have it over this, I cannot do this. This is probably the biggest mistake that I see right here. Make sure you do not do this. If I am multiplying and I have them to negative exponents, I can put them together to the negative exponent. But once again, if there is an addition sign, that's a different operation, and I cannot do that. Okay, so here's just some examples in the end showing us that how we can prove that those don't work. So again, this is just showing you that it does not work. Okay, so this is the last voiceover for this week, and I hope these are helpful, and I will talk with you soon.